Previously, we saw how to construct geometry and generate 2D structured mesh along an aerofoil. Now, let us move on to the Fluent setup. Now we need to specify the boundary conditions or what type of boundary conditions we are going to provide during in the Fluent setup. So in order to do that, the boundary conditions are given to the edges of the computational domain. So this front will be the velocity inlet, the top will be the top inlet, inlet, back outlet, and our negative aerofoil shape will be wall. So we'll just give it aerofoil. So now all of this has been given a boundary condition. Now we need to specify whether all of it is fluid. Now we have already chosen as fluent, so it is not necessary, but I make it a common practice to do so. This provides a reference for fluent in order to justify whether everything is a fluid domain or whether anything is solid or not. Right click on the fluent setup, edit, we are double precision, and we can now specify how many cores do you need to actually solve this. So in parallel I have two cores, so we'll use two. We'll check the mesh in order to see whether there are any negative elements, and there are no negative elements, so this is a valid mesh. Put quality, and the quality is good. So in models we can choose which turbulence model we can use. So right now I'm using the default K omega SST model. In materials it will be air. We can add other materials by edit and create new, such as water and other gas if needed. So currently my Reynolds number which I'll be simulating will be quite low and incompressible fluid. So energy equations and compressibility of air will not be considered. Stop inlet. So beforehand I made a calculation to see whether I'll be simulating a Reynolds number of 1 million. So for that, with a chord of 1 meter, the velocity magnitude is 14.3 meters per second, and I need it in complete x direction. So apply. So currently the angle of attack will be 0, and we can copy this. Edges have also been given as velocity inlets because it is an element complete, a section from which a section of air in which the aerofoil actually moves in. So if we actually edit all others, we can see that the computational, the boundary condition has been copied to all of them. I close. In methods, untick the pseudo time transient, coupled second order, In controls, 200 is fine. In reference values, we need to specify from where it should actually compute. So it will be velocity inlet and initialize. And before that, we need the report definitions. In report definition, we need to specify the lift and drag force. Drag will be on the airfoil, print to console. Now drag is always in the x direction, which is parallel to the incoming velocity. So it's in x direction right now. Lift is perpendicular to the incoming velocity. So airfoil, okay, close. After which we'll run calculation. So we can see that the console is showing stabilizing pressure coupled to enhance linear solver robustness. So in order to overcome this, I have changed the Courant number from 200 to 5, and this is due to the fact that at places our mesh is very coarse and at near the aerofoil it is very fine. So in order to accommodate for the coarseness of the mesh, the Courant number has to be reduced. And then again we will calculate this. Okay. Now we can see that the message has, or the warning has been mitigated. The solution has converged at in less than 200 iterations, which is a good thing. But we can see that the lift coefficient, the value of lift coefficient has not yet stabilized. The drag has somewhat stabilized, but the lift is yet to stabilize. So in order to achieve that, the stable lift coefficient value, will go to monitors, residuals, and show advanced options, and we will convergence criteria will change this from absolute to none, and okay, and then we'll press calculate again. What this does is that it no longer considers the convergence criteria as 10 to the power minus 3 in order for mass conservation and others which are default values, and keeps on calculating. So you can see that the mass has been, continuity has gone below 10 to the power minus 3. Now we can see that the lift coefficient has stabilized somewhat, so we'll stop it here. Now we need to check the contours, velocity. I can see that the maximum velocity is at 17.8 meter per second, so which is not actually in the compressible domain. So you can see that the boundary layer is captured to quite a good extent, as well as the wake region and the pressure. Yes, we can also see that the pressure on the top of the aerofoil is lower than the bottom, which creates lift. Now we need to check whether the pressure around the aerofoil. Yes, we can see that the pressure curve is smooth, and that's it. It's actually quite a good domain. We have, so within this entirety we have imported the coordinates of NACA 2412 aerofoil into design modeler, created a geometry, meshed it, and conducted a simulation for external flow over it.